And a very warm welcome to our first lecture of the day, an introduction to reinforcement learning. So we've played the slot machine game. Let's just briefly reflect on that again. So what was the dilemma that the players faced? Now we discussed this, but it's worth going over it again. So the dilemma was the heart of reinforcement learning. So to win, the players needed to find the best slot machine and then repeatedly pull the handles. But they couldn't find that without exploring the problem space. So that's the dilemma, and it's called the explore-exploit dilemma. So to be a winner, you need to balance exploration and also include some greedy behaviour. You need to exploit the best solutions that you've found. And what you find in practice is if you pursue exclusively one or the other, then you're bound to fail. You're never going to be a winner. So really good news. This is a reinforcement learning problem from artificial intelligence. So for me, this is one of the most exciting research areas for some time, and today we're going to look at the Multiarm Bandit problem, which gives us a sort of subset of reinforcement learning that's quite easy to digest, and we can pick up some of the key concepts that we'll need for some of the more complex parts of reinforcement learning Mike will talk to you about later. So where does reinforcement learning fit within the machine learning landscape? So we've talked earlier in the week about supervised learning. So for example, at its absolute simplest, that might be some sort of classification problem using logistic regression, where you have a large amount of labelled data available to you, and you fit a model to that data, and that's able to discriminate between different groups within your data set. We might also have unsupervised learning, where our data set is unlabeled, and what we're interested in doing is pulling out interesting groups within that, so clusters of data which are related in some way, some spatial relation. So for me, reinforcement learning is quite different to these approaches. For the first reason is you don't need a large data set in order to do reinforcement learning. What you need is an environment and an agent. And that agent will interact with the environment in a fixed set of ways, and the environment provides feedback to that agent that the agent uses to learn. And the agent will have different ways in which it may choose to interact with that environment. So for me, that's drastically different from the other approaches. It opens a whole world of possibilities about how we might do machine learning and artificial intelligence in the future. And I think it will be the big ticket item in terms of artificial intelligence as we go forward. So let's try and imagine our slot machine game as a reinforcement learning problem. So I had some brave volunteers, and we had some slot machines that they were going to play. So a volunteer, let's start with the first volunteer, played the slot machine game. So the first thing they had to do was choose one of the arms to play, and then the arm provided a win or a loss, a 0 or a 1 that went back to the volunteers. And we went round that loop many times. So over time, the volunteers started to build a mental model about the probability of a machine paying out. So they had an internal model about which was the best machine and also how likely the other machines were going to pay out. Now the explore-exploit dilemma comes in there because we're never quite certain that we've just not had a bit of random chance within our selections. So perhaps machine 3 is appearing to be the best at the moment, but actually machine 2 is the best. So what we might do is go and explore machine 2 again by pulling that arm to see what we get. And the more we do that, the clearer picture we'll have about which are the good machines and which are the better machines and which is the best. So this is a reinforcement learning problem. So the volunteers can be thought of as an agent, and our one-arm bandit casino can be thought of as an environment. And the actions the agent was able to take was to play the different bandits, so to select which bandit to play, and the feedback that was provided from the environment can be thought of as a signal, a reward signal. And the agent is interested in accumulating as much reward as it possibly can. And it does that because the agent's got a model of the environment stored internally. And that model, in this case, would just be the payout rate of each of those bandits. So just to go over those terms again, in reinforcement learning problems, you have an agent, and an agent is a goal-directed learner. It has a specific goal that it's trying to achieve. So that's very different from a human player or a human in general in the world, because we have many conflicting objectives, whereas an agent is generally has a single goal that they want to achieve. The agent can sense part of the environment and are able to take limited actions to interact with it. So in this case, it was interacting with the bandit casino by pulling different arms. The environment is a simulated world. Okay, and what's really interesting about this problem is that world can contain uncertainty. So the multi-arm bandit problem that we're going to be looking at is such an environment. So it is uncertain because we don't know if that bandit will pay out or not each time you pull the arm. You don't know in advance. There's a probability, a probabilistic chance of winning or losing. And a key component of reinforcement learning is obviously reward. And if you read more about reinforcement learning, reward will feature quite heavily in the discussions, a reward structure, and what is the best way to set up rewards within your model to get your agent to behave how you want it to behave. In the bandit problem, it's fairly straightforward. It's a 0 or a 1, but in more complex problems, immediate actions may affect chances of reward in the future. So it becomes slightly more complex. And then some agents, some types of reinforcement learning have a model, which is a representation of the environment, which, as we saw, may be imperfect. Other types of reinforcement learning won't have a model. It will do something very different. But for now, it's a simple idea to think that an agent has some sort of internal representation of the external world that it uses to help it make decisions about what actions to take. And I keep saying they. I don't want to give the agent, make you think that this agent is a real person or entity. It's an algorithm. It's an algorithm or some sort of approximator that we're using. So this type of reinforcement learning is a simplification of a wider reinforcement learning problem, and that includes additional complexity. So, for example, taking an action in an environment may change its state. And if that's, so you can think of that as Mike talked about in a lecture earlier this week, where you might want to interact with a simulation model of a healthcare system. So if an action's taken there, you would expect in an hour of simulated time later for the state of the system to be very different. So the multi-arm bandit problem. So it's very simple. So you have a set of bandits. Here we've got 3, and those bandits have payout rates. So we've got 3 bandits here. The first one pays out 30% of the time, the second 70% of the time, and the third 10% of the time. And the multi-arm bandit problem is really trying to find the best bandit. And the type of bandits we'll work with are called Bernoulli bandits. That just means that it returns a 0 or 1 value, a Bernoulli distributed value. So it's worth remembering that this is an online problem, and that means that an agent is going to step forward in time. So it's going to start at time step 1 and take an action, and that action is going to have some consequences, and then the agent will step forward in time again and then take another action, and so on. And each time that action is taken, the environment provides some feedback. That feedback is probabilistic, or in other terms stochastic, so it's uncertain exactly what's going to come back. The other thing about it being an online problem is the agent can only observe the reward of the arm they pulled. So the agent won't know what would have happened if they'd pulled a different arm at that time point. There's no way of them knowing that. And basically, the stochastic side of it comes because we've got a fixed but unknown distribution. So this is just this 10% or 30% payout distribution that we've got. Now this can get more complicated, but for our purposes, we're going to simplify things and work with the stationary bandit problem. So if we flick back a slide, our second bandit has a mean payout rate of 0.7. That won't change over time. That will always be the best bandit. So let's have a think about an odd but practical example of where bandits are used in the real world. And I really love this example because it's something that you perhaps might not expect. So it's used by Netflix, and it's used. So if you're familiar with Netflix, I'm sure many more people are after lockdown. You may or may not have noticed that the artwork that Netflix displays for certain TV and films changes. And you might also know that if you've got multiple accounts in your house, so your children might have a different account from you, your children may be shown a different piece of artwork for the same program as you, from you. So why does Netflix do that? And it's all about bait. It's all about clickbait. So Netflix is interested in what is the optimal artwork to show to different individuals in order to encourage them to watch that movie or watch that TV program. So here we're going to have a look at an example from Stranger Things, which is a TV program produced by Netflix. And obviously the best one here is the picture where they're wearing the Ghostbusters outfit, in my opinion. That's what will get me to click on it. But there are a number of other options that they might use. So how does that work? Well, let's think about an old-fashioned way of doing it first. And this is a bit like a randomized controlled trial. So we'd call this A/B testing. So we'd pick two of the artworks and we'd randomize the audience into two groups. So for example, we might have 1 million viewers in one group and another million in a second group. And then what Netflix would do is they would collect data on the click-through rate. So the number of times that's shown to people and the number of times they click on it. So for example, a result might be that our first artwork is clicked on about 30% of the time, and our second artwork is clicked on 50% of the time. So we pick artwork number 2. Job done. That's it. Perfect. You've got your answer. That's the one you want to show to your audience. However, there is a problem with A/B testing. So we did find the best artwork to maximize our click-through rate, but it was expensive. And it was expensive because we pulled the suboptimal arm a silly number of times, really. So we didn't need to, as we were collecting that data, we were learning information, and we weren't using that information to update the rate at which we showed that artwork to people. So we call that regret. So it's the loss suffered by not showing the optimal artwork. So we can calculate regret for this example retrospectively. So if we've got 1 million viewers in each group and the click-through rates are 0.3 and 0.5, we lost 200,000 views of our program. So Netflix treats the artwork problem as a multi-arm bandit because it wants to minimize regret. It wants people to watch its programs. It doesn't want people to go onto Amazon Prime or Disney Plus or, I don't know, BBC Four and watch something else. So this is a bit of a simplification because, as I hinted at the start, Netflix may show different types of artwork to different groups of people. So they modify the multi-arm bandit problem to something called the Contextual Bandit, and that takes user information into account. So at its simplest, it may show children and adults different imagery for the same program, or it may show male or female different imagery for the same program. So regrets, let's just reflect on that for a moment. So it's the loss suffered by not pulling the optimal arm. So here's a simple calculation rather than worrying about the mathematical notation there. So we know the proportions in each group which click through, and we know the total number of people within the arm that wasn't optimal. So we take the difference between the two proportions and multiply that by the number of people available. So our regret was 200,000. So we lost 200,000 clicks and watches of our video, which is not good. So how do you implement an agent to solve the multi-arm bandit problem? So of course, as you might expect, this is a problem that's been studied for many years, and there's a huge number of algorithms available. And for me, the most attractive is always the simplest, and that is the Epsilon Greedy algorithm. It's basically this code you can see on the screen, or this is pseudocode slightly. Epsilon Greedy works by trying to balance exploration and exploitation in the simplest possible way. So you give Epsilon Greedy a budget, and it's going to basically loop through that budget. So if you give it a budget of 1,000, it's going to perform 1,000 loops of the algorithm. It will sample from the uniform distribution, so a value between 0 and 1, and then it just checks, is that value bigger than a value called epsilon? So if epsilon was 0.2, it would check to see, is your value from the uniform distribution bigger than 0.2? If it is, then we play what we think is the best arm currently. If it isn't, we explore. So you can just think of that as 20% of the time we explore and 80% of the time we exploit. So that 20% just allows that bit of uncertainty in the algorithm to always just check about to see what else might be out there, because suddenly we might find that another arm is actually better. Now there's some downsides to this, because over time we'll have updated so much that we will have a really good idea in a stationary problem which is the best arm. But there's also some benefits if that people's opinions are changing over time, or the effectiveness of a drug is changing over time or something like that. In Epsilon Greedy won't give up, it will still continue to explore over time. But that's basically the whole algorithm. So sample, take a sample and then say, am I going to explore or am I going to exploit? So let's have a look how that works. So here I've set up the Multiarm Bandit problem for our Netflix artwork. So down at the bottom of the screen we've got all of our Netflix artwork. We've got an epsilon of 0.2, so we're going to explore 20% of the time. I'm going to roll a dice, and that's going to decide if I explore or I exploit. And then I'm going to pick one of these artworks to play, perhaps randomly, or it will be the best. And I'm going to keep track of what I think the payouts, the click-through rate from this artwork is. And we're going to see how we home in on the best solution over time by updating. So the first thing I do is I roll a 0.8. So that means I'm going to exploit because it's bigger than 0.2. However, at this point, I've got no information at all. So this is one of the key differences between reinforcement learning and machine learning. I start off and I know nothing about my environment. And then I bring in a general algorithm that I use to learn about my environment and home in on the best actions. So when I've got no information and I want to exploit, I might as well just play the first action in my list, which is what I've done. So I've clicked on this first stranger things artwork, and well, hey, we've won, that's paid out. So I've recorded a win there. So I play again, I roll the dice again, and this time it's come out 0.3. And my algorithm says, okay, if it's bigger than 0.2, I need to exploit. So I go back and I look for what my best is. Well, that's the first one because that's the only one I've got information about. So I play that. And this time, I don't win, I lose. The reward is 0. Let's roll the dice again. So this time I roll 0.5. So because this is less than epsilon, that means I explore. So I randomly choose one of the artworks to play. And I've chosen this one here, the third in the list. So I pull that arm off the bandit. And well, hey, I've won. Okay, so now we've got some more information about our environment. We can see that our best estimate of the click-through rate for the first in the list is 0.5, and now our best estimate of our third in the list is 1. So currently we think this is the best artwork to show our viewers. So let's roll the dice again. Okay, so 0.25, so it's bigger than 0.2, so we exploit. So we play our third in the list again, and this time we've lost. So now we've got a tie in terms of which might be the best payout rate. So we just automatically default that to the first in the list. That's kind of implementation nuance. You may have kept it as the same one, that doesn't matter. Let's roll the dice again and see what happens. Okay, we've got 0.56, which means we exploit. So we've now played the best in the list again, which is number 1, and we've lost again. So our click-through rate here has now turned to 0.33. So we've won once out of 3 plays of that bandit. So the third in the list becomes the best again. So we roll the dice, and what do we get? We get a 0.15. So that's less than epsilon, which means we need to explore. So we randomly choose an artwork in the list, and we've chose this one where they're dressed up as the Ghostbusters, and that's clicked through and that's worked. Okay, so we've won. We've got 1. So that's now our best. Okay, so we're gradually starting to explore, and we're also playing what we think is the best bet at each point. Okay, so we roll the dice again, and this time it's 0.75, so we're going to exploit. So we play this artwork again, and we've won again. So we played that twice, and we've won both times, 100% of the time. So our click-through win rate is 1, so it's still our best. So we roll again, 0.66. We play the same artwork because we think it's our best, and we've won again. So we've won 3 out of 3. So we roll again. This time the artwork, we get 0.66, so we're going to exploit, so we play the same artwork, but this time we lose. Okay, so we then update our estimate of the payout rate, and that now drops to 0.75. So we've won 3 out of 4 times on that, but it's still our best. We roll again. This time we get 0.19. Okay, so we now ignore our best and we randomly choose one of the artworks to explore. Now that could be any of the artworks. Yeah, there's nothing hard coded to say we won't randomly select the best, and there's nothing hard coded to say we won't randomly select one of the arms we've already played. But for this contrived example, we are going to choose a different one. So we pick this close-up of the group of kids. Okay, and we play that and we lose. Okay, so we don't think that's a very good arm at the moment. Our payout rate is 0, but we have played it. So let's jump ahead. Okay, so we've jumped ahead now to round 500. So we play this. A bandit would play this many times. So now what can we see? Well, we can see that we've kind of done a fair bit of exploration. So we've got different predicted payout rates. This is our internal model. We've got different payout rates for each of those artworks. And we can see 2 of the artworks are particularly interesting. So we've got the close-up and we've got them dressed as the Ghostbusters, and the payout rates of those is 0.5 and 0.6. So those are 2 which are kind of competing for the best slot. However, we haven't played this artwork at all yet, and that can happen even with 500 rounds. Oops. Okay, so let's play again. And now we're going to jump forward another 500 steps. We're now at round 1000. And we can see we've now played all of the artworks at least once. So we've got estimates of what we think their payout rate is, and we've gradually updated that in an online manner over time. And you'll see that if we drop back to 500, at this point we felt this was our best, so 80% of the time we were going to play this arm until we found a new better one, and that's continued. So we've seen that's been played quite a lot, and our estimate of this second one has dropped somewhat. Okay, so we've played this a few more times and our payout rate there is of 0.3. So over time the algorithm has gradually homed in through reinforcement on its best, on what it feels is the best artwork, and that's really key. So this is an online problem, and each time the algorithm plays, it explores or it exploits, and that's at the heart of reinforcement learning. And eventually it will start reinforcing what it thinks is the best, and it will continue to play that more and more, and that will become a much better estimate of what the true mean of that payout rate is. So we're going to have a look at this in a small Python lab in Spider. The code is going to be more complicated than what we see here. Okay, so we've got some functions already created for you where we can create a custom bandit problem. So these are the mean payout rates of the bandits we used in the game at the start. So we're going to compare how an Epsilon Greedy agent would do compared to how you guys did in our game. So we're going to create some bandit arms. We're going to put them in an environment, a Bernoulli casino, and then we're going to create an Epsilon Greedy agent. We can specify some hyperparameters, so the exploration rate, epsilon, and the budget, and then we just solve with that agent, and then there's going to be a bit of code provided that prints out the reward found, and then we'll visualize what actions the agent took. So just to summarize what we've talked through, the reinforcement learning problem is very different from other paradigms in machine learning. It's also by far the most exciting part of reinforcement of machine learning and AI, in my opinion anyway. It's directly applicable to any form of web analytics and marketing. It's also applicable to trials. You won't see it very often. It tends to be the classic A/B testing approach which is used in trials, but reinforcement learning is a way to run a trial. And so the downside of the A/B testing approach is you're able to identify the best arm, but that typically comes at a high price. So for example, when you're testing a treatment, the price is that you didn't give the best treatment to a certain subgroup of the population. And so one way to set up these sort of experiments is to take an Epsilon Greedy approach. That's a really powerful alternative to A/B testing. There are derivatives to that. What we're going to do is we're going to look at one of those in the Python lab. And just to emphasize, this will be a very simple lab. We're not going to get into writing the code of this ourselves. We're just going to use some pre-written code and look at the performance of it. So I hope you enjoyed that, and I hope you agree that reinforcement learning is an exciting area of AI. And I'll see you in the lab.